So let's go through an example with graphing just a linear function, a linear equation, because this will tie very closely to what we do with linear inequalities with just a little twist or two, kind of like when we were solving the linear inequalities and how similar it is to linear equations. So let's say we graph the equation y equals 2x minus 3. So what's going to be helpful is having slope-intercept form. So when we have this y equals 2x minus 3, we have a slope of 2, and what'll be helpful is to think of that as 2 over 1. So again, the slope is giving me directions with that numerator telling me how we move up or down. So since that's a positive 2, that's telling me to move up 2. And then the denominator tells me how to move left and right. So that positive 1 would be telling me to move to the right 1. So it gives me a little map to follow there. And then the y-intercept gives me a coordinate to graph. So with that b equals -3, that gives me a coordinate of 0, -3. So with the coordinate and the slope as a map to a second coordinate, we can start graphing this line. So I'm going to plot the point at 0, -3, and then I'm going to follow this up to right 1 trend. Up to right 1, up to right 1. And I'm just going to grab some extra points so my graph is nice and clear. And then we connect those with a straight line. And then we'd have arrows going off to infinity since that line's going to continue forever. So when we graph a linear equation, in terms of solutions to the linear equation, absolutely everything along this line is a solution. So that's what the graph of a line is it's this visual representation of all of these possible answers. So I have these coordinates of all these dots that I drew, but also everything in between, like something kind of messy like 1.50. That would be a coordinate, and anything like whatever decimals are happening at that point where it's between like kind of nice places on the grid, those are solutions too. So if we wanted to check solutions, like is 5, 3 a solution? So what we would do is we would go look at the coordinate 5, 3. So let's see, 4, 5, 3. That is not landing on the line, so that would be not a solution. So no. Is 0, 0 a solution? Well, we'll go to our graph, and 0, 0 is not along the line, so that is also not a solution. So all of the coordinates that are not along the line are not solutions, and all of the points on the line, so like 2, 1 would be a solution, 3, 3 would be a solution, all of those. Okay, so now we have that review, let's talk about graphing linear inequalities. So graphing linear inequalities, we're going to follow those same steps of using slope and intercept. Something we'll need to pay attention to is the type of line we draw. We're going to have two types of lines. We're going to have a dotted line and a solid line. And it's going to depend on what our inequality symbol is. So if we have the strictly more than, strictly less than, meaning we don't have the equals part, we're going to use this kind of dashed or dotted line. So it's going to look something like this, just a dashed line to show that that line is a barrier, but our solutions are not actually included on that line. And then if we're using the symbol more than or equal to, less than or equal to, we're going to use a solid line, just like we do with linear equations, to show that solutions along the line are in fact solutions because we have it equals. All right, and then our next step will be to shade either above or below the line, depending on which way our inequality is facing. So it's all about y values. So when you think about what we're looking for, think about the outputs, and that this whole idea of looking for y less than something, y more than something, it's going to give us a direction of whether we want to go basically up or down in terms of our y-axis. So let's look at a few examples and we'll talk about that piece because that can be kind of hard to instinctively understand. So Let's start with this y is less than or equal to 2x minus 3. So we actually graphed 2x minus 3 up above. So we'd go through the same steps. Again, we're using this slope of 2 over 1, a y-intercept of negative 3. So that gives me a coordinate and then a map to follow of a slope of 2. So I'm going to plot all those points. And then because this is an inequality, before I connect those dots, I just need to pause for a moment and check what symbol are we using. So because this is less than or equal to, we're going to use a solid line to show that we can land on that line itself. All right, so this graph should look exactly the same as up above for y equals 2x minus 3. But what we want to include is y less than or equal to 2x minus 3. So there's a few ways to think about this, and I'll mention this each time, and I'll kind of describe different ways to go about it. What I find helpful is just looking at like a single point along the line, especially the line along the y-axis, at least for me, is easier to visualize. So let's say I focus on this 0, negative 3, and the fact that we either want to be shading up or down. And in terms of y values, going up is going to represent larger values, and going down is going to represent smaller values. And because our function wants less than or equal to, what I want to do is shade downward. So what I like to do is draw myself a little arrow to show we're going to draw in this downward direction. So what I'm going to do is shade in. Let me grab my big highlighter pen, and I'm going to shade in all of this because everything in this region is a solution. So we end up shading below the line because we're looking at less than or equal to. So let's check out those solutions that we saw up above where we asked, is 5, 3 a solution? Is 0, 0 a solution? So visually, 5, 3, so let's see, 5, 3 is landing here, and it's landing in this shaded region. So that's going to be a yes. But let's actually show that algebraically. So this is where y is 3, and we're saying that's less than or equal to 2 times 5 minus 3. So 3 is less than or equal to 10 minus 3, which is 7. And that's a true statement. 3 is in fact less than 7. So that one's all good. Now 0, 0, notice that's not in the shaded region. So this is not going to be a solution. And to prove that algebraically, it would be plugging in 0 less than or equal to 2 times 0 minus 3. So we'd be saying 0 is less than or equal to negative 3. And that is false. 0 is not less than or equal to negative 3. So with solutions with a linear inequality, in this case, we're getting the solutions along the line, but also all of these solutions in the region where y is less than or equal to that line. So that line's acting as a barrier. I do want to show you in Desmos. If we go to Desmos, graphing, we can graph these lines. So if I go y less than or equal to, and there's a special symbol on the keyboard that's within Desmos, or you can just type in the less than symbol and then the equal sign, and it automatically changes the symbol. And then you can see it's graphing the line as well as the shaded region. So if you're unsure about which side to be drawing on, you can use that as a guide. All right, let's look at a few more examples here. So y is more than or equal to negative 4/3 x plus 1. So my slope is a negative 4/3. I'm just going to attach the negative to the 4 in the numerator. So in terms of directions, this is telling me to go down 4, right 3. And then we also have the coordinate from our y-intercept of 0, positive 1. Okay, so I'm going to graph 0, 1. And let's see, we're going to go down 4. So 1, 2, 3, 4, right 3. And I'm just going to grab a few more points. Down 4, right 3, 3, 4, and that'll do it. And let's see, I'm going to check my symbol to know whether it's a solid line or a dashed line. Because this is more than or equal to, we're going to use a solid line. I'm just going to connect those, and I'm just going to extend it so it goes to the edge of my paper. Or not edge of my paper, but edge of my grid. All right, and then arrows at the end to show that it continues on. So now I want to evaluate, do I shade above and or below? And with this one, we want y is more than or equal to this line. So that's going to be shading in the upward direction. So again, visually, if it's hard to see that, I like to go to the y-intercept and just think about either going up or down. And because we want more than here, we want the larger y values. So we're going to shade upwards. So I'm going to grab my big highlighter and shade all of that region in to show all of our solutions are equal to that line and landing above that line. Okay, what if we're given this x plus 4y is more than 8? And it's not in slope-intercept form, then what we need to do is we need to solve for y. So I'm going to subtract x from both sides. So that'll be 8 minus x. Divide both sides by 4, so y is more than, so 8 divided by 4 is 2. And then this negative x divided by 4, I'm going to write that as negative 1/4 x. So then I can see my slope of negative 1/4. And we can see our y-intercept of positive 2. So the slope is telling me to go down 1, right 4. So we're going to graph 0, positive 2, and then do this slope of down 1, right 4. Down 1, right 4, and then a few in the other direction too. All right, then I pause and check what symbol are we using. So this is y is just more than. Since we don't have the equals, then what we're going to do is show a dashed line. So I'm going to connect those with a dotted line to show that this is a barrier, that this line of 2 minus 1/4 x is a barrier for our region, but we're not equal to that line. So the points along that line are not solutions. All right, so we want the y values more than this line, so that means we're going to be shading above the line. And there's our solution. All right, so that's how we graph given these linear inequalities. And it's just a matter of evaluating that symbol to know what type of line you're using, and then shading above or below based on the direction of the symbol. Let's take a look at an application. So we have a store sells peanuts for $4 per pound and cashews for $8 per pound. And they plan to sell a new mixed nut blend in a jar. What combinations of peanuts and cashews are possible if they want the mix to cost $6 or less? So let's use the variable p for the number of peanuts. Ooh, actually, since we're going to graph this, let's use x and y. And it doesn't matter which is x and which is y here. So let's do x is the number of peanuts and y is the number of cashews. All right. So in terms of finding the cost, so the cost is going to come from, let's see, $4 for each, to be pounds of peanuts, not necessarily they're not counting the individual peanuts. So pounds of peanuts, pounds of cashews. So for peanuts, the cost will be $4 per pound. So that would be 4 times x. And then we add on the cost of the cashews, which is $8 per pound. So 8 times y. So we want this cost to be $6 or less. So if we calculate this cost of 4x plus 8y, we want this to be less than or equal to $6. Okay, so in order to graph this, what we're going to do is solve for y. So I'm going to subtract 4x from both sides. So we have y is less than or equal to 6 minus 4x. And then I'm going to divide both sides by 8, which means we'll have y is less than or equal to, let's see, 6 over 8 will reduce down to a 3/4. And then minus 4 over 8 is a 1/2 times x. So y is less than or equal to 3/4 minus 1/2 x. Okay, so graphing this. I'm just thinking about how I want to set up my axes here. So I'm going to set up my x and y axes. And since I want to graph at 3/4, actually, I'm going to do the intercept method here, just to get an idea of 2 points to graph. So I'm going to do is look at what happens when x is 0 and what happens when y is 0. So if I plug in x equals 0, I get that y-intercept of 3/4. So that gives me an idea of my y-axis. And then if y is equal to 0, let's see, if y is equal to 0, we would have 0. I'm just going to do equals 3/4 minus 1/2 x. That would be 1/2 x equals 3/4. Multiply both sides by 2, so x is equal to 3/2. Okay, so what I'm going to do is I'm going to go ahead and say 8 units is equal to 1. So this is a half, this is 3/4, which we want to graph, and this is along my y-axis, and then let's see, that would be 1/4. I'm going to do the same thing along the x-axis. So 4 units is going to be equal to a half. And that should give me a nice visual of the possibilities. So let's see, this is, 1/2, 1, 1.5, 2, and that should be all that we need. All right, so my 2 points that I'm going to plot, 0, 3/4, and 3/2, 0. And we're going to connect those. And we want all of the combinations where y is less than or equal to this. So I'd be shading below. And notice also with this word problem, there are kind of these other implied inequalities. The fact that y should probably be more than or equal to 0 and x should probably be more than or equal to 0. So what that's going to have me do is basically only shade in the first quadrant, because this is a word problem and we won't have negative values coming through. So what I'm going to do is just shade this region below the line, but also above the x-axis and to the right of the y-axis. So we end up with this triangle, and we get these corner points. And then in terms of what the solutions are, because what their question was, what combinations of peanuts and cashews are available, we have a visual representation of those solutions, because there's infinite possibilities. Like the most extreme would be to have no peanuts and no cashews. Yeah, that would cost less than $6 because it would cost nothing. But then we could do like a half pound of peanuts and no cashews. We could do a half pound of cashews and no peanuts. So we get these values along the x and y axes. We get all of these values in the middle there, and we also get these values along the line that we graphed.